Hello there, and welcome to our sleepy journey through the cosmos. I'm so glad you found your way here tonight, perhaps after a long day when your mind feels too active to settle, or maybe you're someone who finds peace in the vast mysteries that sparkle above us each evening. Either way, you've come to the right place. Tonight, we're embarking on a gentle exploration of 100 fascinating facts about stars. These aren't just distant points of light, but incredible cosmic furnaces, ancient storytellers, and the very architects of everything we know. Some of what you'll discover may surprise you. Others will settle into your thoughts like soft starlight, perfect companions for drifting towards sleep. Before we begin our celestial voyage, if these peaceful explorations help you unwind or spark your curiosity about the universe, consider subscribing and letting me know in the comments which stellar facts fascinate you most. It helps others find their way to these quiet cosmic conversations. Now get comfortable, let your breathing slow, and allow your mind to wander among the stars as we uncover their hidden secrets, one gentle fact at a time. Stars are not actually star-shaped. Despite every drawing you've ever seen, real stars are massive spheres of burning gas, perfectly round due to their own gravity pulling equally in all directions. The twinkling points we see are simply how our atmosphere bends their light as it travels across space to reach our eyes. The nearest star to Earth is much closer than you might think. While we often talk about distant stars, our own Sun is actually a star sitting just 93 million miles away. The next closest star, Proxima Centauri, is over 4 light-years distant, meaning light from that star takes 4 years to reach us, compared to just 8 minutes from our Sun. Most stars in the universe are actually quite small and dim. While we notice the bright giants in our night sky, the majority of stars are red dwarfs, much smaller and cooler than our Sun. These modest stellar citizens can burn for trillions of years, far longer than the universe has even existed so far. Stars are born inside vast clouds of gas and dust called nebulae. These cosmic nurseries can stretch for hundreds of light years, filled with the raw materials needed to create new suns. When gravity pulls these materials together tightly enough, the pressure and heat eventually ignite nuclear fusion, and a star begins to shine. The largest known star could hold over 5 billion of our suns inside it. Scuti, a red supergiant, is so enormous that if it replaced our Sun, its surface would extend beyond the orbit of Jupiter. Yet despite its incredible size, it contains only about 30 times the mass of our Sun, making it surprisingly wispy and delicate. Stars come in a rainbow of colors that reveal their temperature. The hottest stars burn blue-white at over 50,000 degrees Fahrenheit, while the coolest glow red at around 5,000 degrees. Our Sun, with its yellow light, sits comfortably in the middle at about 10,000 degrees on its surface. Some stars are so dense that a teaspoon of their material would weigh as much as a mountain. These neutron stars form when massive stars collapse, crushing matter so tightly that protons and electrons merge into neutrons. The entire star, though only about 12 miles across, can contain more mass than our Sun. Binary stars are actually more common than single stars like our Sun. About half of all stars have at least one companion, locked in gravitational dances that can last billions of years. Some of these stellar couples orbit each other in hours, while others take millennia to complete a single waltz around their partner. Stars can steal material from their neighbors in a cosmic form of stellar vampirism. When two stars orbit closely, the larger one can strip gas from its companion, growing brighter while its partner slowly fades. This process can even cause spectacular explosions when the stolen material suddenly ignites on the surface of the receiving star. The light from some stars left them before humans existed on Earth. When you look at distant stars, you're literally seeing into the past. The light from Deneb, visible in summer skies, began its journey toward Earth about 2,600 years ago, when the ancient Greeks were just beginning to study the heavens. Stars can spin incredibly fast, completing rotations in mere minutes. While our Sun takes about 25 days to rotate once, some neutron stars spin hundreds of times per second, their magnetic fields whipping through space like cosmic lighthouses, creating pulses we can detect from Earth. Some stars are older than most. Galaxies in the universe, the oldest known star, HD 140283, formed when the universe was just a cosmic infant. This ancient stellar citizen has been burning for nearly 14 billion years, having witnessed the formation of galaxies, planets, and, eventually, life itself. Stars create and scatter the elements that make planets and life possible. Inside their nuclear furnaces, stars fuse hydrogen into helium, then helium into carbon, oxygen, and heavier elements. When massive stars die in supernova explosions, they scatter these materials into space, providing the building blocks for future worlds. Variable stars change their brightness in predictable patterns, acting as cosmic lighthouses. Some grow brighter and dimmer over days or years, while others pulse like stellar heartbeats. Astronomers use these predictable changes to measure distances across the galaxy and understand stellar physics. The smallest stars burn the longest, like cosmic tortoises in the stellar race. Red dwarf stars, though only a fraction of our Sun's size, can burn steadily for trillions of years. Meanwhile, the most massive stars live fast and die young, exhausting their fuel in just millions of years before exploding as supernovae. Stars can be thrown out of galaxies like cosmic cannonballs. When binary stars get too close to a supermassive black hole, one star can be flung away at incredible speeds, traveling millions of miles per hour as it escapes into intergalactic space, forever wandering alone in the cosmic void. Brown dwarfs are failed stars that never quite manage to ignite. These stellar wannabes formed like regular stars but didn't gather enough mass to start nuclear fusion in their cores. They glow dimly from their own heat, slowly cooling over billions of years, like cosmic embers. Some stars are so massive they skip the usual stellar death and collapse directly into black holes. When stars over 25 times the mass of our Sun reach the end of their lives, they don't explode as supernovae. Instead, they simply disappear, creating black holes in a cosmic vanishing act. Stars can form planets made almost entirely of diamond. In certain stellar systems where carbon is abundant, the extreme pressure and unique chemistry can create worlds composed largely of crystallized carbon. These diamond planets would be dazzling to behold, though they'd be far too hot and hostile for any earthly visitor. The magnetic fields of some stars are trillions of times stronger than Earth's. Magnetars, a special type of neutron star, possess magnetic fields so powerful they could erase a credit card from halfway across the solar system. These fields are strong enough to distort the very atoms that make up matter. Stars can cannibalize each other in gravitational battles spanning millions of years. When two stars of different sizes orbit closely, the larger one gradually strips material from its smaller companion. Eventually, the smaller star may be completely consumed, leaving behind only a single, bloated survivor. Some stellar explosions can be seen from billions of light-years away. Gamma-ray bursts thought to occur when the most massive stars collapse into black holes, release more energy in seconds than our Sun will produce in its entire 10 billion year lifetime. These cosmic beacons can briefly outshine entire galaxies. Stars near the center of our galaxy experience time differently due to gravitational effects. Einstein's relativity tells us that strong gravity slows time, so stars orbiting close to our galaxy's supermassive black hole experience seconds slightly differently than we do on Earth, though the difference is incredibly small. The surface of some stars is cooler than a campfire. Brown dwarfs and the coolest red dwarfs can have surface temperatures as low as 1,800 degrees Fahrenheit. While still incredibly hot by human standards, this is actually cooler than molten lava and barely hot enough to appear red to our eyes. Stars can form in clusters containing millions of siblings, all born from the same cosmic cloud. These stellar cities, called globular clusters, contain some of the oldest stars in the galaxy. Over billions of years, gravitational interactions slowly scatter the stars, sending them on individual journeys through space. The chemistry of a star determines its entire life story, from birth to death. Stars with more heavy elements, which astronomers call metals, tend to form planets more easily. Meanwhile, the very first stars in the universe contained almost no heavy elements at all, making them fundamentally different from every star we see today. Some stars are so close together they share a common atmosphere. In these contact binary systems, two stars literally touch, creating a peanut-shaped object with two cores. Material flows between them in complex patterns, sometimes causing one star to rejuvenate while the other ages, creating stellar couples with dramatically different apparent ages. Wolf-Rayet stars are among the most extreme objects in the universe. These stellar behemoths have blown away their outer layers, exposing cores so hot they shine with temperatures over 100,000 degrees. They blast powerful stellar winds into space at speeds of several thousand miles per second, creating beautiful nebulae around themselves. Stars can survive having their outer layers completely stripped away. When this happens, we're left with a white-hot stellar core called a white dwarf. These stellar remnants are incredibly dense, containing about as much mass as our Sun compressed into a sphere the size of Earth, and they'll glow for billions of years as they slowly cool. The Sun loses about 4 million tons of mass every second through nuclear fusion. As hydrogen atoms fuse to create helium in the Sun's core, a tiny amount of mass converts to energy according to Einstein's famous equation. This missing mass becomes the light and heat that makes life on Earth possible. Some stars pulsate like cosmic drums, expanding and contracting in regular rhythms. Cepheid variable stars brighten and dim in cycles that can last days or months. Astronomers use these stellar metronomes as standard candles to measure distances across the galaxy, since their pulsation period directly relates to their true brightness, red. Giant stars can grow so large they engulf their own planets. When stars like our Sun begin to run out of fuel, they swell dramatically, sometimes reaching sizes hundreds of times larger than their original dimensions. Any planets orbiting too closely get swallowed up in the star's expanded atmosphere. The cores of massive stars become like Russian nesting dolls of different elements. As the star burns through its fuel, it creates layers of different materials. Hydrogen burning in the outermost shell, helium deeper in, then carbon, oxygen, silicon, and finally iron at the very center, each layer burning at increasingly higher temperatures. Some stars are magnetic powerhouses that can affect space weather across light years. When these magnetic stars undergo starquakes or experience flares, they release bursts of energy that can disrupt electronics even at interstellar distances. Their magnetic fields are so strong they could kill you from thousands of miles away. Stars can be invisible twins hiding in plain sight. Many stars that appear single to our eyes are actually binary systems, where one star is much brighter than the other, or where the stars are so close they appear as a single point of light. Advanced techniques reveal that most stars have hidden companions we never suspected. The most massive stars forge elements all the way up to iron in their cores. But elements heavier than iron, like gold and uranium, require even more extreme conditions. These precious metals are created in the final explosive moments of a star's life, during supernovae or when neutron stars collide, making every gold ring a product of stellar death. Tauri stars are stellar toddlers still throwing cosmic tantrums. These young stars, less than 10 million years old, are still settling down after their formation. They vary wildly in brightness, shoot jets of material into space, and are often surrounded by spinning disks of gas and dust that may eventually form planets. Some stars rotate so fast they become flattened like cosmic pancakes. The most rapidly spinning stars can complete a rotation in just a few hours compared to our Sun's leisurely 25-day spin. This extreme rotation flattens them significantly, making them wider at their equators than at their poles. Stars can focus light like natural gravitational lenses. When a star passes exactly between Earth and a more distant star, its gravity bends the background star's light, causing it to brighten dramatically. This gravitational microlensing effect has revealed thousands of hidden planets orbiting distant stars. Blue supergiant stars live life in the fast lane, burning incredibly hot and bright. These stellar speedsters can be 50,000 times brighter than our Sun and have surface temperatures exceeding 40,000 degrees. They consume their fuel so rapidly that they only live a few million years before ending their lives in spectacular supernova explosions. The stellar graveyard of our galaxy contains billions of white dwarf stars. These stellar corpses, each about the size of Earth but containing the mass of the Sun, slowly cool over billions of years. Eventually they'll become cold, dark objects called black dwarfs, though the universe isn't old enough for any to exist. Yet stars can be ejected from their birthplace at incredible speeds. When massive stars form in dense clusters, gravitational interactions can fling some of them away at speeds of hundreds of miles per second. These runaway stars race through the galaxy, leaving bow shocks in the interstellar medium like boats, cutting through water. Some stars are so perfectly spherical they could serve as cosmic pool balls. Kepler 1145123 is the roundest natural object ever discovered, varying by only a few miles between its equatorial and polar diameters despite being twice the size of our Sun. This near-perfect sphere spins very slowly, taking more than 100 days to complete one rotation. Stellar nurseries can birth stars for millions of years from the same cloud of gas. The Eagle Nebula and similar star-forming regions contain enough material to create thousands of stars over extended periods. As each generation of stars forms, their energy and stellar winds sculpt the remaining gas into fantastic shapes, creating the pillars and caverns we see in space photographs. Stars can steal planets from each other during close encounters. When two stellar systems pass nearby, the gravitational tug-of-war can rip planets away from their parent stars and send them wandering through space as rogue worlds, or capture them into orbits around new suns. These planetary kidnappings reshape entire solar systems. The most ancient stars in our galaxy are time capsules from the universe's youth. Population 3. Stars, if any, still exist, would contain almost no heavy elements composed of nearly pure hydrogen and helium left over from the Big Bang. Finding one of these stellar fossils would provide a direct window into the cosmic dark ages. Some stars explode multiple times before finally dying. Luminous blue variables like Eta Carinae undergo massive eruptions that can temporarily make them among the brightest stars in the galaxy, only to fade and then potentially explode, again years or decades later. These stellar drama queens keep astronomers guessing about their ultimate fate. Binary star systems can create some of the most beautiful objects in space. When one star in a binary pair dies and becomes a white dwarf, it can strip companion, this stolen material from its living. A glowing ACC gas forms Narration disk around the white dwarf, creating spectacular displays of cosmic light and occasionally triggering nova explosions. Stars near supermassive black holes experience extreme tidal forces that can stretch them like cosmic taffy. Some unfortunate stars that venture too close get torn apart in a process called spaghettification, their material forming a bright accretion disk around the black hole that can outshine entire galaxies for months. The Sun's magnetic field reverses completely every 11 years in a cycle that affects space weather throughout the solar system. During solar maximum, increased magnetic activity causes more sunspots, solar flares, and coronal mass ejections that can disrupt satellites and create aurora displays on Earth. Red dwarf stars make up about 75% of all stars in the galaxy, yet none are visible to the naked eye. These small, cool stars are so dim that even the closest ones require telescopes to see. However, their incredible longevity means they'll be the last stars shining when the universe grows old and dark. Stars can form natural particle accelerators more powerful than anything humans have built. The magnetic fields around neutron stars and some other exotic stellar objects can accelerate particles to nearly the speed of light, creating cosmic rays that travel across the galaxy and occasionally strike Earth's atmosphere. Some stellar explosions create elements that shouldn't exist according to our understanding of nuclear physics. In the extreme conditions of certain supernova, scientists have detected isotopes and elements that challenge our models of how matter behaves under the most intense pressures and temperatures in the universe. Stars can be born already middle-aged if they form from recycled stellar material. When previous generations of stars die and scatter their processed elements into space, new stars that form from this enriched material start their lives with heavy elements already present, affecting their color, temperature, and evolutionary path. The stellar wind from our Sun creates a bubble around the entire solar system called the heliosphere. This invisible boundary, extending far beyond Pluto, protects us from some cosmic radiation and marks the edge of our Sun's influence, where interstellar space begins and the solar wind finally meets resistance from the galaxy's magnetic field. Stars can cannibalize their own planets during their death throes. As stars evolve into red giants, they don't just engulf nearby planets, they can also gravitationally disrupt the orbits of more distant worlds, causing them to spiral inward and be consumed, adding their material to the dying star's outer layers. Some stars contain exotic matter that exists nowhere else in the universe. Inside neutron stars, the incredible pressure creates forms of matter that can't exist under any earthly conditions. Scientists theorize there might be quark matter, strange matter, or even more exotic states that defy our understanding of physics, locked away in these stellar remnants. The light from distant stars carries the signature of planets we've never seen. When a planet passes in front of its star from our perspective, it creates a tiny dip in the star's brightness. By studying these subtle changes, astronomers have discovered thousands of exoplanets, some potentially harboring conditions suitable for life as we know it. Stars can be used as cosmic GPS systems to navigate through space. Pulsars, with their incredibly regular pulses, serve as natural beacons that spacecraft can use for navigation. The timing of these stellar lighthouses is so precise that they could guide future interstellar missions across the vast emptiness between star systems. Some stars have atmospheres made of exotic materials like titanium and vanadium. In the hottest stellar atmospheres, temperatures are so extreme that metals that would be solid rocks on Earth exist as gases, creating spectral signatures that reveal the incredible conditions on these distant worlds. Binary stars can age at completely different rates due to mass transfer. When one star steals material from its companion, the thief can actually become younger and hotter while its victim ages rapidly. This stellar rejuvenation can make binary pairs appear to have impossible age differences. The cores of the most massive stars become so hot they begin destroying the very elements they created. At temperatures exceeding 3 billion degrees, gamma rays become so energetic they can split apart iron nuclei, causing the star's core to collapse catastrophically as it essentially eats itself from the inside out. Some stars are perfectly camouflaged, hiding in plain sight among their neighbors. Certain white dwarf stars have atmospheres so pure they appear almost invisible against the background of space, detectable only by their gravitational effects on nearby objects or the subtle way they bend light from more distant stars. Stars can form natural time machines by warping space around them. The intense gravity of neutron stars and other compact objects slows time so dramatically that astronauts orbiting close to these stellar remnants would age noticeably slower than people on Earth, experiencing the universe at a different rate. Magnetospheres around some stars create natural radio transmitters broadcasting across the galaxy. These stellar radio signals, generated by charged particles spiraling around magnetic field lines, can be detected from thousands of light years away, essentially making these stars into cosmic radio stations. The death of massive stars can trigger the birth of new stellar generations. Supernova shock waves compress nearby gas clouds, causing them to collapse and form new stars. In this way, stellar death becomes stellar birth, with each generation of stars seeding the materials and energy needed for the next. Some stars exist in such extreme environments they challenge our understanding of stellar physics. Stars orbiting close to supermassive black holes experience gravitational fields so intense that their very structure is altered, creating objects that behave unlike any stars in quieter regions of space. Red dwarf flare stars can suddenly brighten by factors of thousands in minutes. These stellar temper tantrums release enormous amounts of energy in X-rays and ultraviolet light, potentially sterilizing the atmospheres of any nearby planets and making these common stars surprisingly hostile to potential life. Stars can act as natural laboratories for studying matter under impossible conditions. The interiors of different stellar types recreate environments that we could never achieve on Earth, from the diamond rain that may fall in certain stellar atmospheres to the superfluid neutron matter in stellar cores. Some binary stars are so close they orbit each other in less time than it takes to watch a movie. These ultra-compact binaries with orbital periods measured in minutes are spiraling ever closer together, destined to merge in violent collisions that will reshape both stars completely. The stellar winds from the hottest stars can strip atmospheres from planets hundreds of times farther away than Earth is from the Sun. These cosmic hurricanes, moving at thousands of miles per second, create vast cavities in space and can completely alter the evolution of entire planetary systems. Stars can survive being partially consumed by black holes, emerging as strange hybrid objects. In rare cases, when a star's orbit around a black hole is just right, it can have its outer layers stripped away while its core survives, creating an exotic stellar remnant unlike anything else in the universe. The magnetic fields of some stars are so complex they create natural particle accelerators in space. These stellar machines can boost charged particles to incredible energies, creating cosmic ray showers that traverse the galaxy and occasionally rain down on Earth's atmosphere as invisible stellar messengers. Stellar archaeology reveals the history of our galaxy through the chemistry of ancient stars. By analyzing the elements present in the oldest stars, astronomers can piece together the story of how our galaxy formed and evolved, reading the cosmic fossil record written in starlight. Some stars pulsate in multiple rhythms simultaneously, like cosmic orchestras playing complex harmonies. These multimode pulsators vary their brightness according to several different periods at once, creating intricate patterns that reveal the internal structure of the star through stellar seismology. The formation of the heaviest elements requires conditions so extreme they may only occur when neutron stars collide. These rare cosmic crashes, called kilonovae, forge gold, platinum, and uranium in quantities that could supply entire galaxies, making every precious metal a product of stellar catastrophe. Stars can be gravitationally focused into natural telescopes by massive objects. When a star's gravity bends light from a more distant object, it can create magnifications of thousands or millions of times, potentially allowing us to see details across the universe that would otherwise be impossible to observe. The surfaces of some stars are covered in starquakes that release more energy than all human civilization has ever produced. These stellar tremors, caused by adjustments in the star's magnetic field or internal structure, can crack the ultra-hard surface of neutron stars and send shockwaves rippling through space. Binary millisecond pulsars are among the most precise clocks in the universe. These rapidly spinning stellar remnants, spun up by stealing material from companion stars, keep time so accurately they rival atomic clocks, making them perfect tools for testing Einstein's theories and searching for gravitational waves. Some stars have been observed to disappear completely from the sky without any warning. These stellar vanishing acts might represent stars collapsing directly into black holes, bypassing the usual supernova explosion, or they could indicate stellar mergers that create entirely new types of objects. The stellar nurseries, where stars are born, contain complex organic molecules that could be the building blocks of life. In the cold, dense regions where stars form, simple atoms combine to create amino acids, sugars, and other compounds that, when delivered to planets by asteroids and comets, could seed entire worlds with prebiotic chemistry. Stars can be stripped of their outer layers by tidal forces, revealing their hot, dense cores while still alive. These helium stars, created when binary interactions remove a star's hydrogen envelope, burn with intense blue light and represent a completely different evolutionary path than solitary stars follow. The most luminous stars in the universe shine with the power of millions of suns combined. These hypergiant stars are so bright they slowly destroy themselves through radiation pressure, blowing away their outer layers in spectacular stellar winds that can be seen from across the galaxy. Some stellar systems contain planets made of materials that don't exist naturally on Earth. In systems with unusual chemistry, planets can form from pure carbon, creating diamond worlds, or from other exotic combinations of elements that produce landscapes unlike anything in our solar system. Stars near the galactic center move so fast they complete orbits in just decades, rather than the millions of years typical for most stellar orbits. These high-speed stars, whipping around our galaxy's supermassive black hole, provide direct tests of Einstein's general relativity in the strongest gravitational field we can observe. The coolest known stars have surface temperatures lower than a pizza oven. These ultra-cool brown dwarfs with temperatures around 200 degrees Celsius blur the line between stars and planets, glowing faintly in infrared light while remaining completely invisible to human eyes. Some stars are born already dying, formed, with so little mass they can never sustain nuclear fusion. These failed stars, brown dwarfs, glow only from the heat of their initial formation and slowly cool over billions of years, eventually becoming cold, dark objects wandering invisibly through space. Stellar collisions in dense clusters can create blue stars merge in crow-straggler stars that appear impossibly young. When two smaller-did environments, they combine their fuel reserves and appear much younger and bluer than other stars of the same age, creating stellar puzzles that challenged astronomers for decades. The light echoes from some stellar explosions can be observed years after the initial event. When a supernova's light reflects off surrounding dust clouds, we can see the explosion angles. As from multiple, the reflected light reaches us, providing a three-dimensional view of these cosmic catastrophes. Stars can harbor hidden companions that reveal themselves only when they steal material from their host. These vampire stars remain invisible until they begin feeding, creating sudden brightness increases that can make a seemingly normal star appear to explode, only to fade back to obscurity when the feeding stops. Some stars generate their own weather systems with stellar hurricanes and magnetic tornadoes. The complex magnetic fields of active stars create phenomena analogous to terrestrial weather, but on scales that dwarf anything on Earth, with storms that could engulf entire planets and magnetic tornadoes that stretch for millions of miles. Most rapidly rotating neutron stars spin faster than kitchen blenders, completing hundreds of rotations per second. These millisecond pulsars are among the most extreme objects in the universe, with surfaces moving at significant fractions of the speed of light while remaining perfectly spherical despite the incredible centrifugal forces. Stars can be born from the collision of entire galaxies, triggered when gas clouds from different stellar systems collide and compress. These galactic encounters can spark massive bursts of star formation, creating brilliant starburst regions that outshine the combined light of billions of normal stars. Some stellar remnants are so massive they shouldn't exist according to our current theories. Neutron stars with masses approaching 3 times that of our Sun push the boundaries of what matter can withstand before collapsing into black holes, suggesting we still don't fully understand the extreme physics of stellar death. The magnetic fields of magnetars can distort the very atoms that make up matter, stretching electron orbitals into cigar shapes and creating forms of matter that exist nowhere else in the universe. These stellar magnetic monsters represent some of the most extreme conditions physics allows. Stars can focus cosmic rays into deadly beams that sweep across space like lighthouse beacons. The magnetic fields around pulsars accelerate particles to nearly the speed of light, creating radiation beams so intense they could be lethal to any spacecraft unlucky enough to cross their path, even from distances of light years. Binary stars can create natural particle accelerators more powerful than any human-built machine. When stellar winds from 2 stars collide at high speed, they create shock fronts that accelerate particles to incredible energies, generating cosmic rays that travel across the galaxy and occasionally reach Earth as invisible stellar messengers. Some stars exist in systems so chaotic that predicting their behavior becomes impossible. Triple and multiple star systems can undergo complex gravitational interactions that lead to unpredictable stellar ejections, collisions, and orbital changes, creating cosmic ballet performances that unfold over millions of years with outcomes that cannot be calculated in advance. As our cosmic journey through these stellar secrets draws toward its close, let your mind drift like starlight across the gentle darkness of space. Each fact we've shared is like a distant sun glowing softly in the vast catalogue of cosmic wonders, each one a reminder that the universe is far stranger and more beautiful than we ever imagined. The oldest light in the universe still bathes us in its gentle glow every moment of every day. The cosmic microwave background radiation, left over from the Big Bang itself, washes over Earth constantly, carrying with it the faint warmth of creation itself. This ancient starlight, stretched and cooled by billions of years of cosmic expansion, whispers the story of the universe's birth to anyone with the right instruments to listen. Some stars are born as twins, but end their lives as completely different beings. Binary stars that begin with similar masses can evolve along drastically different paths depending on their distance from each other. One might become a red giant while its companion remains a main sequence star, or one could explode as a supernova while the other continues burning peacefully for billions more years. The hearts of certain stars beat with rhythms more regular than the finest Swiss timepieces. Pulsating stellar metronomes keep time across the galaxy. Variables expand and contract with such precision that astronomers use them as standard candles to measure cosmic distances. These, their rhythmic brightness, changes marking the passage of cosmic ages with mathematical precision. Stars can be born from the ashes of their own ancestors in an endless cycle of cosmic reincarnation. When massive stars die in supernova explosions, they scatter heavy elements into space, enriching the interstellar medium with the building blocks needed for new stars. These second and third generation stars inherit the processed materials from their predecessors, carrying forward the chemical legacy of stellar death and rebirth. Some stellar nurseries are so active they give birth to thousands of stars simultaneously in cosmic baby booms. These starburst regions, triggered by galactic collisions or shockwaves from nearby supernovae, can create more new stars in a few million years than our entire galaxy typically produces in a billion years, lighting up vast regions of space with the brilliant glow of stellar infancy. Runaway stars race through the galaxy at speeds that would carry them from Earth to the Moon in just a few hours. These stellar speedsters, ejected from their birth clusters by gravitational interactions or supernova explosions, plow through the interstellar medium at velocities of hundreds of kilometers per second, creating bow shocks and trailing stellar winds behind them like cosmic comets. The surfaces of some neutron stars are so smooth they make the finest mirrors look rough by comparison. Despite their incredible density and magnetic fields, these stellar remnants maintain surfaces that vary by only millimeters across their entire diameter, creating the most perfectly spherical objects known to exist in nature, smoother than anything humans could ever manufacture. Binary stars can engage in gravitational warfare that lasts for millions of years. When two stars of different masses orbit each other closely, they can exchange material back and forth in complex patterns, sometimes reversing roles, as the initially smaller star grows larger by stealing mass from its companion, creating stellar relationships more complicated than any soap opera. Some stars manufacture diamonds in their cores through nuclear alchemy. In the intense pressures and temperatures of stellar interiors, carbon atoms can be compressed and arranged into crystalline structures, creating diamonds the size of planets floating in seas of liquid metallic hydrogen, treasures that will never see the light of day until the star dies. The magnetic field lines of certain stars twist and reconnect in explosions more powerful than a billion hydrogen bombs. These stellar flares release tremendous bursts of energy across the electromagnetic spectrum, creating temporary aurora that can envelop entire planets and disrupting the delicate balance of stellar atmospheres with violent magnetic storms. Stars near the edge of our galaxy move through space like cosmic pioneers exploring the frontier between our island universe and the vast emptiness beyond. These boundary stars experience different gravitational influences than their inner galaxy cousins, following elongated orbits that carry them far above and below the galactic plane on journeys lasting hundreds of millions of years. Some stellar explosions create shock waves that continue expanding for thousands of years after the initial blast. These supernova remnants, visible as glowing shells of hot gas, plow through the interstellar medium like cosmic snowplows, compressing and heating the material they encounter while gradually slowing down until they finally merge with the surrounding space. The cores of massive stars become cosmic pressure cookers, where the normal rules of chemistry break down completely. At temperatures exceeding billions of degrees and pressures trillions of times greater than Earth's atmosphere, atomic nuclei are forced together in fusion reactions that create increasingly heavy elements, building the periodic table one stellar generation at a time. Binary millisecond pulsars create natural laboratories for testing the fundamental laws of physics. These systems, where a rapidly spinning neutron star orbits closely with a companion, allow scientists to observe the effects of extreme gravity, test Einstein's theories of relativity, and search for gravitational waves with precision that rivals our most sophisticated instruments. Some stars are so old they contain metals forged in the cores of the very first generation of stars that ever existed. These ancient stellar citizens carry in their atmospheres the processed remains of population 3 stars, the universe's first suns that contained almost no heavy elements when they formed from primordial hydrogen and helium in the cosmic dark ages. Stellar winds from the most massive stars can carve cathedral-sized cavities in the interstellar medium. These hot, fast-moving streams of charged particles hollow out vast bubbles in space, creating empty regions hundreds of light-years across where new stars cannot form until the stellar wind weakens and allows gas to flow back in. The rotation of some stars is so perfectly synchronized with their orbital motion that they always show the same face to their companion. Like the Moon's relationship with Earth, these tidally locked stellar couples have synchronized their spins with their orbits, creating systems where eternal day and eternal night exist on opposite hemispheres of each star. Neutron-star collisions create ripples in space-time itself that can be detected from billions of light-years away. When these ultra-dense stellar remnants spiral into each other, they convert a significant fraction of their mass directly into gravitational waves, sending disturbances through the fabric of the universe that stretch and compress space itself as they pass. Some stars exist in such crowded neighborhoods that close encounters with neighbors regularly reshape their orbits. In dense globular clusters containing hundreds of thousands of stars, gravitational interactions can fling stars out of the cluster entirely, capture them into new binary systems, or alter their evolutionary paths in ways impossible for isolated stars. The light from certain variable stars changes not just in brightness, but in color as they pulsate. These chromatic variables cycle through different hues as their surfaces heat and cool during expansion and contraction cycles, creating stellar light shows where individual stars shift from red to yellow to blue and back again over periods ranging from hours to years. Star formation can be triggered by the passage of spiral density waves that sweep through galaxies like slow-motion tsunamis. These gravitational disturbances compress interstellar gas clouds as they pass, initiating collapse and starbirth in their wake, creating cosmic clocks that tick with the orbital rhythm of distant suns. The atmosphere in stellar cores. Some stars undergo helium flash events that temporarily make them thousands of times brighter than normal. These stellar hiccups occur when helium fusion ignites explosively in the cores of certain evolved stars, creating brief periods of incredible luminosity that can outshine entire galaxies for a few days before the star settles back into a more stable burning phase. The magnetic fields around certain stars create natural dynamos that generate radio emissions detectable across interstellar distances. These stellar radio transmitters broadcast their signals throughout the galaxy, creating a cosmic cacophony of electromagnetic noise that radio telescopes can tune into like stations on a celestial radio dial. Binary white dwarf systems can explode, as type Ia supernovae with such consistent brightness that they serve as standard candles for measuring cosmic distances. These stellar explosions, triggered when one white dwarf steals enough material from its companion to exceed a critical mass threshold, all reach nearly the same peak luminosity, making them cosmic mile markers for mapping the expansion of the universe. Some neutron stars have crusts made of materials so exotic they exist nowhere else in nature. The outer layers of these stellar remnants contain nuclei with far more neutrons than protons, creating isotopes that would instantly decay under normal conditions but remain stable under the crushing gravitational pressure of neutron star surfaces. The stellar winds from dying red giant stars create some of the most beautiful structures in space as they interact with previously ejected material. These planetary nebulae, despite their name having nothing to do with planets, showcase the artistic side of stellar death as expanding shells of glowing gas create cosmic sculptures that can be seen from thousands of light years away. Stars can be captured by passing black holes and forced into highly elliptical orbits that carry them from the cold outer regions of space into the searing environment near the event horizon. These gravitational prisoners experience extreme tidal forces during their closest approaches, sometimes having materials stripped away in spectacular displays of cosmic violence. The cores of massive stars can become so hot that gamma-ray photons spontaneously convert into matter and antimatter particle pairs. This photodisintegration process essentially causes the star to consume its own energy, leading to catastrophic core collapse as the radiation pressure that was supporting the star against gravity suddenly vanishes. Some stellar remnants are composed entirely of quarks, the fundamental building blocks of protons and neutrons, compressed into forms of matter that may not exist anywhere else in the universe. These hypothetical quark stars would be even denser than neutron stars, representing the ultimate compression of matter before it collapses into a black hole. Binary systems can create natural particle accelerators when stellar winds from two stars collide at relativistic speeds. These cosmic collision zones generate shock fronts that accelerate charged particles to energies exceeding those produced in the most powerful human-built accelerators, creating cosmic rays that travel across the galaxy as messengers from distant stellar interactions. The surfaces of some stars experience weather patterns with magnetic storms that dwarf anything on Earth. Stellar hurricanes can span areas larger than Jupiter's Great Red Spot, driven by convective currents that transport energy from the stellar core to the surface in turbulent cells that create patterns visible in high-resolution stellar observations. Ancient globular clusters contain stellar populations that formed when the universe was young and the galaxy was still assembling. These stellar time capsules preserve examples of stars with chemical compositions reflecting the primordial abundance of elements, providing direct observational links to the conditions that existed during cosmic dawn when the first stellar cities were born. Some binary stars experience mutual eclipses so total that their combined light drops to nearly zero for hours at a time. These deeply eclipsing binaries create natural experiments in stellar astrophysics, allowing astronomers to measure stellar masses, radii, and temperatures with extraordinary precision by analyzing the exact timing and depth of these cosmic shadow plays. The death spirals of binary neutron stars can be observed as the orbital periods gradually decrease due to energy loss through gravitational wave radiation. These systems are slowly spiraling toward inevitable collision, losing orbital energy at exactly the rate predicted by Einstein's general relativity, providing some of the most precise confirmations of our understanding of space-time physics. Stellar nurseries contain complex chemistry laboratories where simple molecules combine to form the organic building blocks of life. In the cold, dense regions where stars are born, carbon-based compounds including amino acids, sugars, and even primitive proteins form naturally, suggesting that the ingredients for life may be distributed throughout star-forming regions across the galaxy. Some stars are born already spinning so rapidly they're nearly torn apart by centrifugal forces. These break-up velocities, where the star's rotation rate approaches the point where material at the equator would be flung into space, create severely flattened stellar shapes and complex magnetic field geometries that affect every aspect of the star's evolution and energy output. The gravitational lensing effect of massive stars can magnify the light from more distant objects by factors of millions, creating natural cosmic telescopes. When a foreground star passes precisely between Earth and a background star, its gravity focuses the distant light and can reveal details about planetary systems, stellar companions, and even individual objects that would otherwise be completely invisible. As these stellar secrets continue to unfold in the quiet darkness around you, let each fact settle gently into your thoughts like distant starlight reaching Earth after traveling for eons across the cosmic void. The universe of stars is vast and full of wonders we've only begun to explore, each discovery revealing new mysteries that beckon us deeper into the infinite depths of space and time. Magnetars can unleash energy bursts that would be lethal from the distance of the moon. These ultra-magnetized neutron stars occasionally experience starquakes that crack their incredibly hard crusts, suddenly releasing magnetic energy equivalent to all the power humanity has ever generated. The resulting gamma-ray flares can temporarily blind X-ray satellites and disrupt radio communications across entire hemispheres of Earth, even from distances of tens of thousands of light years. Some stars exist in gravitational dance partnerships, so complex that three-body physics makes their long-term behavior fundamentally unpredictable. These chaotic triple-star systems can evolve along countless different paths, with tiny changes in initial conditions leading to vastly different outcomes over millions of years. One slight variation might result in a stable configuration lasting violent stellar ejections or billions of years, while another could lead to catastrophic collisions. The stellar graveyard of white dwarf stars slowly crystallizes over cosmic time into the largest diamonds in the universe. As these stellar remnants cool over billions of years, the carbon and oxygen in their cores arrange themselves into crystalline structures, creating diamond spheres the size of Earth. These cosmic gems will continue growing more perfect as they cool, eventually becoming cold, dark treasures drifting through space long after the last star has died. Brown dwarf stars create their own faint aurora displays as charged particles interact with their magnetic fields. Despite being failed stars that never achieved nuclear fusion, these stellar wannabes generate enough magnetic activity to accelerate particles and create glowing atmospheric phenomena similar to Earth's northern lights, though visible only in infrared wavelengths that human eyes cannot detect. Some stellar systems harbor planets with multiple suns that create impossibly complex patterns of day and night. In these circumbinary worlds, sunrises and sunsets can involve two or more stars of different colors rising and setting at different times, creating alien skies where shadows can point in multiple directions and seasons depend on the orbital mechanics of multiple stellar companions dancing through space. The collision of neutron stars creates conditions so extreme they forge elements that cannot be made anywhere else in the universe. These kilonova events produce more gold in a few seconds than our sun could create in its entire lifetime, scattering precious metals across space in expanding clouds that eventually seed new stellar systems with the raw materials for rocky planets, and potentially life itself. Stellar stars can strip entire winds from the most lumin atmospheres from planets hundreds of astronomical units away. These cosmic gales, moving at thousands of miles per second, create vast hollow shells around the most massive stars, preventing planet formation in enormous volumes of space and ensuring that any worlds unfortunate enough to form in these regions remain barren and airless. Some binary stars can rejuvenate each other through gravitational interactions that mix fresh hydrogen into their cores. This stellar cannibalization can make ancient stars appear impossibly young, creating blue straggler stars that seem to violate everything we know about stellar evolution by burning brighter and hotter than they should given their age and original mass. The most rapidly rotating stars complete full rotations in less time than it takes to boil water. These stellar speed demons, spinning at nearly their breakup velocity, experience such extreme centrifugal forces that they become severely flattened, with equatorial diameters significantly larger than their polar diameters, conditions impossible to replicate anywhere else, creating natural stellar laboratory. Hypervelocity stars race through the galaxy at speeds exceeding the escape velocity of flung from the galactic center by the Milky Way itself. These stellar refugees' encounters with supermassive black holes are intergalactic space, carrying with them the chemical signatures of our, and wander forever through the emptiness of destined to eventually leave our galaxy entirely cosmic home, the magnetic field. Reversals of some stars create natural particle accelerators that generate cosmic rays more energetic than anything produced in human-built machines. Them on journeys across the galaxy that made particles to velocities approaching the speed of light, launching. These stellar magnetic reconnection events can boost charge, eventually bring them crashing into Earth's atmosphere as invisible messengers from distant stellar catastrophes. Wolf-Rayet stars blow away their entire outer atmospheres in stellar winds so powerful they illuminate surrounding nebulae across dozens of light years. These stripped stellar cores, burning at temperatures exceeding 50,000 degrees Celsius, create some of the most spectacular sights in the galaxy as their expelled material collides with surrounding gas clouds, painting cosmic masterpieces in glowing hydrogen and ionized oxygen, transforming from quiet, stable. Some stars undergo dramatic personality changes as they age. These stellar Jekyll and Hyde transformations occur, suns into violent, unpredictable variable pulsations and brightness variations that can make when internal changes in structure cause massive instabilities, leading to eruptions, previously invisible stars suddenly become one of the brightest objects in the sky. Binary millisecond pulsars can be spun up to rotation rates of over 700 times per second through accretion of material from companion stars. These recycled pulsars, given new life by stellar vampirism, become some of the most precise timekeepers in the universe, with rotation periods stable enough to rival atomic clocks and detect the subtle effects of gravitational waves passing through space. The cores of massive stars become cosmic furnaces where silicon burning creates iron peak elements in a nuclear cascade that ultimately leads to stellar death. As each successive fusion stage produces less energy while requiring higher temperatures, the star races toward its final moments when iron ash accumulates in the core until nuclear, the star against gravitational collapse. Some fusion can no longer support stellar nurseries are trigger nova explosions, creating chain interactivity by the shock waves from nearby sup reactions of star formation that can propagate fall in sequences spanning millions of years across entire spiral arms. These stellar domin, as each generation of massive stars lives briefly and dies explosively, triggering the birth of new stellar populations in a cosmic cycle of death and rebirth. Contact binary stars literally touch each other, sharing a common atmosphere in gravitational embraces so tight they appear as single peanut-shaped objects. These stellar lovers exchange material through their touching surfaces, creating complex flows of hot gas that can cause dramatic changes in brightness and color as the stars evolve together in ways impossible for isolated stellar objects. The tidal forces near neutron stars are so extreme they could stretch a human body into a strand of atoms before the person could fall more than a few feet. These gravitational gradients, millions of times stronger than anything experienced on Earth, demonstrate the incredible density packed into objects only a few miles across, but containing more mass than our entire Sun. Stellar archaeology reveals that some ancient stars contain uranium and thorium created in supernova explosions that occurred before our solar system formed. By measuring the current abundances of these radioactive elements and calculating their decay rates, astronomers can determine ages for the oldest stars in our galaxy, some of which began shining when the universe was less than 1 billion years. Some stars experience thermal pulses that cause them to dramatically expand and contract over thousands of years in breathing motions visible across interstellar distances. These asymptotic giant branch stars puff off shells of material during each pulse, creating intricate patterns of concentric rings that mark the rhythm of stellar evolution like growth rings in cosmic trees. The stellar winds from red supergiant. Stars can carry away more mass in a single year than our Sun contains in total. These gentle giants, despite their relatively cool surface temperatures, lose material so rapidly that they can shed entire solar masses over just thousands of years, dramatically altering their evolutionary path and ultimate fate as they race toward supernova explosions. Neutron star starquakes release more energy in a fraction of a second than our Sun produces in an entire year. These sudden adjustments in the ultra-rigid crusts of neutron stars occur when magnetic field changes cause the surface to crack and readjust, sending seismic waves around the star at significant fractions of the speed of light and launching gamma-ray bursts that can be detected across the galaxy. Some binary star systems experience novae explosions that recur with clockwork regularity over decades or centuries. These stellar time bombs accumulate material from companion stars until reaching critical thresholds for explosive hydrogen burning, then blow away their accumulated layers in brilliant flashes before beginning the cycle anew, creating predictable fireworks shows in the night sky. The formation of the first stars in the universe required gas clouds to cool through mechanisms, completely different from modern star formation. Without heavy elements to radiate away heat efficiently, primordial star formation depended on molecular hydrogen cooling, creating conditions that favored the formation of much more massive stars than typically formed today, leading to an early universe populated by stellar giants. Stellar collisions in dense globular clusters can create blue straggler stars that appear to have discovered the fountain of youth. When two smaller stars merge in these crowded stellar environments, they combine their nuclear fuel reserves and emerge as single objects that appear much younger and more massive than other cluster members, creating stellar puzzles that challenged astronomers for generations. The magnetic fields of some stars are so tangled and complex, they create natural dynamos generating radio emissions that vary unpredictably over time, scales from seconds to years. These stellar radio sources broadcast across multiple frequencies simultaneously, creating electromagnetic signatures that can be detected by radio telescopes as far away as neighboring galaxies, making them beacons for studying magnetic field physics under extreme conditions. Planets orbiting close to certain types of variable stars experience climates that change dramatically as their host stars brighten and dim. These worlds undergo ice ages and greenhouse periods lasting months or years as stellar luminosity variations alter the amount of energy reaching their surfaces, creating environments where evolution would face constant adaptation challenges. Unlike anything experienced on Earth, some stellar explosions create cavities in the interstellar medium so large they can encompass hundreds of star systems. These superbubbles, carved out by the combined effects of stellar winds and supernova shockwaves from entire associations of massive stars, create vast empty regions where the density of gas is thousands of times lower than the galactic average, fundamentally altering the structure of their galactic neighborhoods. Stretched across hundreds of degrees of sky, preserve the orbital characteristics and stellar populations of disrupted clusters, allowing astronomers to reconstruct the dynamical history of our galaxy's gravitational evolution. Over cosmic time, some stars are born with magnetic fields already frozen into their structure during formation, creating magnetic fossil fields that persist throughout their entire lifetimes. These magnetic, chemically peculiar stars rotate slowly and maintain organized field geometries that concentrate specific elements in their atmospheres according to magnetic field strength, creating natural laboratories for studying atomic physics. Under conditions impossible to replicate on Earth, the deaths of the most massive stars can trigger gamma-ray bursts so intense they could sterilize entire galactic regions of potential life. These cosmic death rays, focused into narrow beams by the magnetic fields of collapsing stellar cores, release more energy in seconds than most stars produce in millions of years, creating lethal radiation environments that could affect planetary atmospheres across white dwarf systems spire thousands of light years. Binarialing toward merger create some of the most promising sources for future gravitational wave detectors. As these stellar remnants lose orbital energy through gravitational radiation, they gradually approach each other over millions of years, eventually merging in events that will be detectable by space-based gravitational wave observatories as they monitor the slow motion in spiral of these cosmic dancers. The surfaces of neutron stars may be covered with mountains only inches tall, but containing more mass than Earth's entire mountain ranges. The incredible surface gravity of these stellar remnants, billions of times stronger than Earth's, prevents any significant topographical features from forming, creating surfaces so smooth they make billiard balls look rough by comparison, while still containing enormous amounts of compressed matter. Some stellar nurseries contain water mazes that amplify microwave radiation like cosmic laser beams, creating natural amplifiers that can boost signals by factors of millions. These interstellar lighthouses, powered by energy from nearby forming stars, create bright radio sources that can be detected across the galaxy, providing unique probes of the physical conditions in star-forming regions and the early stages of stellar evolution. The chemical composition of stars reveals the galactic recycling program that has operated for billions of years as successive generations of stars have processed and redistributed elements throughout the Milky Way. By studying stellar spectra across different stellar populations, astronomers can trace how the galaxy's metallicity has increased over time, following the gradual enrichment of space with heavy elements forged in stellar cores and scattered by supernova explosions. Stellar rotation can be used as a cosmic clock to determine the ages of stars through gyrochronology, the relationship between rotation rate and stellar age. As stars age, magnetic braking gradually slows their rotation, creating a predictable decline in spin rate that can be calibrated against other age indicators to provide estimates of stellar ages for objects too old to show other evolutionary changes. Some binary stars create natural laboratories for testing exotic physics by generating conditions that cannot be achieved anywhere else in the universe. The extreme gravitational fields, magnetic strengths, and particle densities found in these systems allow astronomers to probe fundamental physics in regimes where classical theories break down and quantum effects become important, providing unique insights into the nature of matter and energy under extreme conditions. The stellar winds from asymptotic giant branch stars carry complex organic molecules into interstellar space, seeding the galaxy with the chemical building blocks necessary for life. These dying stars act as cosmic gardeners, dispersing carbon-based compounds including polycyclic aromatic hydrocarbons and primitive organic polymers that can eventually be incorporated into forming planetary systems, potentially providing prebiotic chemistry to young worlds throughout the galaxy. Millisecond pulsars in binary systems can be used as natural laboratories for testing general relativity with extraordinary precision. The orbital decay rates of these systems due to gravitational wave emission match Einstein's predictions to better than 1 part in 1,000, providing some of the most stringent tests of our understanding of space-time physics and confirming that massive objects really do create ripples in the fabric of the universe itself. The formation of stellar black holes through direct collapse may occur without the dramatic fireworks of supernova explosions, creating failed supernovae where massive stars simply vanish from the sky. These quiet, stellar deaths, where the core collapse proceeds so rapidly that no explosion occurs, may be more common than previously thought and could explain observations of stars that appear to disappear without trace from astronomical surveys. Some stars exist in hierarchical multiple systems with orbital periods ranging from hours to millions of years, creating complex gravitational choreographies that can persist for billions of years. These stellar families, containing 3, 4, or even more members, experience intricate dynamical interactions that can lead to stellar mergers, ejections, or the formation of exotic objects like blue stragglers through gravitational encounters between family members. The magnetic reconnection events in stellar corona can accelerate particles to relativistic energies, creating natural particle accelerators that dwarf anything humans have constructed. These stellar flares release tremendous amounts of energy in seconds, heating coronal plasma to temperatures of hundreds of millions of degrees and launching high-energy particles into interplanetary space at significant fractions of the speed of light. Binary evolution can create some of the most unusual objects in the universe, including helium stars, carbon-oxygen white dwarfs with helium companions, and exotic systems where normal stellar evolution rules are completely rewritten. These evolutionary pathways, available only to stars in close binary systems, produce stellar populations with properties that would be impossible for isolated stars, creating natural laboratories for studying stellar physics under extreme conditions. The tidal heating of planets in close binary star systems can create worlds with volcanic activity far exceeding anything seen in our solar system. These tidally tormented planets, subjected to constantly changing gravitational forces as they orbit between two stars, experience internal heating that can maintain molten surfaces and active geology for billions of years, potentially creating unique environments where life might adapt to extreme conditions. Some stellar associations are so young that astronomers can observe star formation happening in real time through changes in infrared brightness and spectral characteristics. These stellar nurseries, still actively forming new stars from surrounding gas clouds, provide direct observational evidence of how stellar birth proceeds, allowing scientists to test theoretical models of star formation against actual observations of the process as it unfolds. The space between binary stars can become filled with circumbinary material that creates complex accretion dynamics unlike anything seen in single star systems. This shared envelope evolution can lead to dramatic changes in both stars simultaneously, creating common envelope phases where the binary system becomes temporarily surrounded by a dense shell of ejected material that influences the subsequent evolution of both stellar components. Stellar archaeology using the oldest stars in our galaxy has revealed that the Milky Way formed through the merger of smaller proto-galactic fragments, each contributing their own distinct stellar populations with unique chemical signatures. By studying the orbital characteristics and elemental abundances of ancient halo stars, astronomers can reconstruct the assembly history of our galaxy and identify the stellar fossils left behind by long-disrupted dwarf galaxies that helped build the modern Milky Way. The discovery of planets around pulsar stars has revealed that planetary systems can survive even the most violent stellar evolution phases, demonstrating the remarkable resilience of orbital mechanics under extreme conditions. These pulsar planets, bathed in deadly radiation and subjected to intense magnetic fields, represent some of the most hostile environments imaginable, yet somehow maintain stable orbits through their host star's transformation from a normal star to a neutron star remnant. As these final stellar secrets drift through your consciousness like gentle cosmic whispers, let them settle softly into the quiet spaces of your mind. Each star we've encountered tonight carries its own story, its own mystery, its own contribution to the vast tapestry of the universe. Some burn quietly for trillions of years, others explode in brilliant displays that can be seen across cosmic distances, but all play their part in the endless dance of creation and destruction that shapes our cosmos. The stellar realm extends far beyond what we can see with our eyes, encompassing objects so strange and conditions so extreme they challenge our understanding of physics itself. From the diamond hearts of cooling white dwarfs to the magnetic maelstroms surrounding neutron stars, from the gentle stellar winds that carry organic molecules across space to the violent explosions that forge heavy elements in stellar furnaces, the universe of stars reveals itself as endlessly creative, endlessly surprising, and endlessly beautiful. In the vast catalogue of stellar phenomena, we find not just the mechanisms that power the universe, but also the origins of everything familiar. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were forged in the nuclear furnaces of ancient stars and scattered into space by stellar winds and supernova explosions. We are not merely observers of the stellar universe. We are participants in it, made from the very materials processed in stellar cores billions of years ago. As your thoughts begin to drift like interstellar dust clouds caught in the gentle radiation pressure of distant suns, remember that above you right now, countless stellar dramas are unfolding across the galaxy. Binary stars are exchanging material in gravitational embraces. Neutron stars are spinning with clockwork precision. Massive stars are racing toward explosive deaths. And in stellar nurseries throughout the Milky Way, new suns are igniting for the first time, beginning their own billion-year journeys through the cosmos. The night sky that arches over you contains multitudes, not just the few thousand stars visible to human eyes, but hundreds of billions of stellar citizens, each following its own evolutionary path, each contributing its own voice to the cosmic symphony that has been playing since the universe began. In that vast stellar orchestra, our own sun is but a single instrument, yet it provides the energy that makes all earthly life possible, connecting us intimately to the grand stellar community that fills our galaxy. Tonight, as sleep approaches, on gentle stellar winds, let your mind wander freely among these cosmic wonders. Perhaps you'll dream of diamond planets orbiting carbon stars, or find yourself drifting through the magnetosphere of a pulsar, or watching from a safe distance, as binary neutron stars spiral toward their spectacular merger. In the realm of dreams, the impossible becomes possible, and the stellar universe opens its arms to welcome your imagination into spaces where physics becomes poetry and science becomes wonder. The stars will continue their ancient dances long after you wake, continuing the cosmic story that began with the universe's first light and will continue until the last red dwarf finally fades to darkness in the unimaginably distant future. But for now, in this quiet moment between waking and sleep, you carry within your thoughts a small piece of that stellar knowledge, a collection of cosmic secrets that connect you to the vast, luminous, ever-changing universe of stars. Sweet dreams, fellow traveler of the cosmos. May your rest be peaceful and your dreams filled with starlight. And as your consciousness begins to drift like cosmic dust caught in the gentle pull of stellar gravity, let these final stellar revelations settle into the quiet spaces of your mind. Each fact is like a distant star glowing softly in the vast constellation of knowledge, reminding us that the universe holds wonders beyond our wildest imagination. Some stellar remnants retain memories of their former lives in ways we're only beginning to understand. White dwarf stars, the cooling cores of sun-like stars, can maintain crystalline structures in their interiors that preserve the rotational history and magnetic field patterns of their parent stars. These stellar fossils carry forward the angular momentum and magnetic signatures of their former selves, creating objects that bridge the gap between stellar life and death in ways that blur the boundaries between past and present. The surfaces of certain evolved stars experience weather patterns that would dwarf any terrestrial storm system. Red supergiants develop convection cells larger than Earth's orbit, creating granulation patterns visible even from interstellar distances. These stellar weather systems transport energy from the deep interior to the surface in turbulent columns of rising and falling gas, creating temperature variations that cause the star's brightness to fluctuate in complex, unpredictable patterns that can persist for decades. Binary star formation can create natural selection pressures that favor certain stellar masses and orbital configurations. When multiple stars form from the same gas cloud, gravitational interactions during the early formation phase can eject some stars while keeping others bound in stable pairs. This process acts like a cosmic sorting mechanism, creating binary populations with characteristic mass ratios and separation distances that reflect the initial conditions in the stellar nursery. Some neutron stars possess magnetic fields so perfectly organized they create natural waveguides for electromagnetic radiation. These magnetospheric structures channel radio waves and high-energy particles along precise paths, creating beams of radiation that sweep through space with lighthouse-like regularity. The magnetic field geometry of these objects is so complex, it requires three-dimensional computer simulations to understand how particles move through the twisted field lines surrounding the star. The stellar wind interactions in wide binary systems can create bow shocks and trailing structures that persist for millions of years. When one star in a binary pair evolves to the red giant phase while its companion remains on the main sequence, the different stellar winds create complex hydrodynamic structures in the space between the stars. These interaction regions can accelerate particles and create synchrotron emission detectable by radio telescopes, revealing the invisible architecture of stellar wind collisions. Certain classes of variable stars pulsate in multiple modes simultaneously, creating complex interference patterns in their light curves that reveal the internal structure of the stellar interior. These multimode pulsators act like stellar seismographs, with different pulsation frequencies probing different depths within the star. By analyzing the beating patterns created when multiple oscillation modes interfere with each other, astronomers can map the temperature and density gradients inside distant suns. The formation of planets around binary stars requires a delicate balance of gravitational forces that can either enhance or completely prevent planetary system development. In some configurations, the gravitational perturbations from the binary companion can stir the protoplanetary disk and prevent planets from forming. In others, the same perturbations can help concentrate solid material and accelerate planet formation, creating worlds that could never exist around single stars. Some stellar explosions create cavities in space so large they influence star formation, across entire galactic regions. These superbubbles, carved out by successive generations of massive stars, can grow to encompass volumes hundreds of light-years across. The hot, rarefied gas inside these cosmic caverns has densities thousands of times lower interstellar space than typical, creating vast sterile regions where new star formation cannot occur till the bubble eventually cools and contracts. Tidal forces in extremely close binary systems can synchronize not just the rotation of the stars, but also their magnetic field orientations and stellar activity cycles. These magnetically coupled binaries experience coordinated flare events and spot cycles, with both stars showing synchronized variations in brightness and magnetic activity. The magnetic field lines of the two stars can even connect across the space between them, creating a shared magnetosphere that extends throughout the binary system. Stellar archaeology has revealed that some ancient stars contain isotopic ratios that preserve information about the supernova explosions that enriched their birth clouds. By measuring the precise abundances of radioactive decay products in old stellar atmospheres, astronomers can determine which types of supernovae contributed material to different regions of the early galaxy, creating a detailed map of ancient stellar nucleosynthesis processes. The rotation of massive stars can become so rapid during certain evolutionary phases that they approach the theoretical breakup limit, where centrifugal forces nearly overcome gravity. These critically rotating stars develop complex internal mixing patterns that transport fresh hydrogen fuel dwarfs that will outlive galaxies to the magnificent hypergiants that paint nebulae with their dying breath. Each star we've encountered carries its own ancient story written in light and time. Tonight, you've traveled billions of light years without leaving your bed, exploring diamond worlds and magnetic maelstroms, witnessing stellar births in cosmic nurseries and the spectacular death throes of stellar giants. These aren't just distant phenomena, they're intimate connections to your own existence, for you are quite literally made of star stuff, forged in nuclear furnaces that burned long before Earth was even a whisper in the cosmic dark. Sweet dreams, fellow cosmic wanderer, and may your rest be as peaceful as the gentle glow of starlight.